The Physics of Interplanetary Kai, brought to you by Athavan, Lionel, and Sarmad. Following is a video of kids playing the famous indigenous sport of Kai. At first sight, Kai may seem very similar to volleyball, but actually it is quite different. What is Kai? The background of Kai. Originating in Queensland, Australia, in the Torres Strait Islands tribe, group of people stood in circle singing Kai Wade song or the ball song. Game originally used a dark red oval-shaped fruit from the Kai tree as an object to play Kai with. Equipment. Kai can be played indoors or outdoor, and you need a softball, for example, a beach ball or a tennis ball. Game description: 4 to 8 players per team preferably. Amount of people in game should not be larger than 10. Hand-hitting game in which people try to keep the ball off the ground for as long as they can. Players are approximately 1.5 to 2 meters apart. Ball is thrown into the air and every person hits the ball upwards using their palm in order to pass the ball to others. Hands should be flat when hitting it. Players hit the ball to other participants that are not beside the player hitting the ball. 1 point is given for each count. Scoring. The game is won by the team that is able to maintain the ball in the air the longest and does not allow the ball to land on the ground. If the ball strikes the ground while counting how many times the ball is hit, continue counting. Do not restart counting from 0. Different variations of Kai. Can hit the ball twice, one for control, one to hit to another player. For younger players, ball is hit around head height. For more experienced or older players, ball is hit 1 meter above the height of their head. Try completing the alphabet as you strike the ball to all of the players. Players can sit on the floor while playing the game. Following is a short video of our group playing Kai in slow motion.
In terms of kinematics, Kai can be connected to the concept of relative motion. When the ball is thrown in one direction, the air plays a part in moving the ball's path in a slightly different direction. The ground speed of the ball may change due to the tailwind or headwind that pushes the ball into a different direction. When calculating for the speed of the ball, another object is assigned an inertial frame of reference, which means that it is an object that pretends to be completely still while everything surrounding this object is constantly in motion. This helps assess the motion of the ball relative to what the object assumes is moving. In Kai, this can be found when a person who is not part of the striking or catching end is the inertial frame of reference. The speed that they assume the ball is moving at will be different to the speed that the catcher believes the ball is moving at. Relative motion can be used to calculate the speed at which the player needs to hit the ball so that it reaches another player when taking wind speed into account. That way, the player does not lose control of their hit on the ball, which can make the ball move uncontrollably around the field. Being unable to take wind speed into account forces the player receiving the catch to drop the ball, delaying the amount of points the group gets in Kai. Kinematics is involved heavily in Kai as it involves hitting the ball, which contains both vertical and horizontal components. In terms of other planets, the gravity on each planet plays a part in how long and how far a striking of the ball will go. The greater the acceleration of gravity, the higher the ball needs to be hit so that the other player, who is most likely 2 meters away, can catch the ball. If the acceleration of gravity is smaller than that of Earth's, then the ball will be able to be hit up to a vertical distance with more ease. In other words, the speed at which the player hits the ball at can be a lot slower on a planet like Pluto so that the ball does not go out of orbit and does not take a long time to land. We can find the speed required for the ball to reach maximum height in 2 seconds after the ball is struck by the player's palm, using the acceleration of gravity for both Jupiter, which is 24.79 meters per second squared, and Pluto, which is 0.62 meters per second squared. I can do this by using the acceleration formula, which is the sum of the initial and final speeds divided by the time it takes for the ball to reach maximum height. Isolating for the initial speed will give an equation of acceleration times time minus final speed. Since the final vertical speed at maximum height is 0 meters per second, then the initial vertical speed would equal acceleration times time. Using this formula shows that the ball needs to be hit at a speed of 49.58 meters per second to reach its maximum height in 2 seconds on Jupiter. And on Pluto, the ball needs to be hit at a speed of 1.24 meters per second for it to reach maximum height in 2 seconds. Let's take a look at a particular scenario that deals with relative motion. During a game of Kai, the player wishes to hit the ball from one corner of a square to another corner of a square 2 meters away in the northeast direction. The velocity of the ball relative to the air is 5.9 meters per second northeast, and the wind's velocity is 7.1 meters per second east. Using those two components, what would be the ground velocity of the ball? When drawing a diagram of the ball's airspeed and the speed of the air, it shows that the velocity of the ball relative to the ground, or the ground speed, is in the northwest direction. To find out what the resultant ground velocity of the ball is, the velocities need to be broken down into horizontal and vertical components. Also, a certain direction needs to be put as the positive direction, which is east and north in this case. The horizontal ground speed can be found by subtracting the horizontal airspeed of the ball by the horizontal speed of the wind, which results in a velocity of about 2.93 meters per second west. Similarly, the vertical ground speed can be found by subtracting the vertical airspeed of the ball by the vertical speed of the wind, leading to a vertical velocity of approximately 4.17 meters per second north. Now that we have both the horizontal and vertical speeds of the ball's ground speed, drawing a new diagram shows that the ball is indeed in the northwest direction. The resultant speed can be calculated by finding the squares of the horizontal and vertical ground speeds, then adding them, and then finding the square root of that sum. Doing those steps will give you a resultant speed of about 5.1 meters per second. To find the direction, use the diagram that you created and use the tangent formula of the opposite side divided by the adjacent side. That results in an angle of 35 degrees. Therefore, the ground velocity of the ball in order to reach the other player is 5.1 meters per second north, 35 degrees west. In a real-life game of Kai, no magnetism is used even for variations. However, if magnetism were to be connected to the sport, there could be applications to make Kai more interesting, particularly with the field the players are playing on. Magnetism can be applied to Kai by assuming that the players are playing on a magnetic field with a magnetized ball. For instance, if the player wanted to try striking the ball to the opposite side of the playing field, it would be too difficult to simply aim the ball to the other corner, as the magnetic force may cause the ball to be pushed sideways in a circular motion. Since the magnetic force is perpendicular to the direction of the velocity of the ball, centripetal force is produced. Hence, the magnetic force is equal to the centripetal force in this case. In order to get the ball across, the ball needs to have a low magnitude of charge, or the ball needs to be hit at a greater speed. The reason why is because the radius in which the ball moves in a circular path due to centripetal force is directly proportional to the speed of the ball in meters per second, and is inversely proportional to the magnitude of the charge of the ball in coulombs. The greater the speed or the lower the charge, the more the ball will curve at a greater radius so that it reaches the other player. In addition, the ball needs to be hit as if it is initially striking a player that is opposite of the direction of the magnetic force. For instance, in the diagram below, the magnetic force is perpendicular to the velocity of the charged ball. Hence, the ball is forced to move counterclockwise due to the magnetic force. To get the ball across, the player would need to hit the ball in the direction of a player on the right of them, in this case, so that the ball curves and ends up in the direction of the player on the opposite corner. Regardless on what planet you are on, example Jupiter or Pluto, it will not impact the magnetic field that the players are playing on, as the acceleration of gravity does not play a role in the magnetic force or centripetal force. As a result, the magnetic force exerted on a ball on a planet with microgravity will be very similar to the magnetic force exerted on a planet with an acceleration of gravity greater than that of Earth. Now, let's put this concept into the form of a magnetism question. 4 people want to play Kai in a rectangular playing field with a magnetic field strength of 1.5 times 10 to the exponent of negative 5 teslas. A tennis ball, which has a mass of 5.7 times 10 to the exponent of negative 2 kilograms, is trying to be hit at a speed of 9.6 meters per second from one corner of a square to the opposite corner. The ball is induced with a charge. The length between the two corners is 2 meters. What is the charge of the magnetized ball? In this case, the magnetic force is perpendicular to the velocity of the charged ball, which indicates that the magnetic force produces a centripetal force. The centripetal force is also equal to the magnetic force. Putting both forces as equal to each other and isolating for the ball's charge, which is Q, gives the equation of Q equals mv over rb. M would equal to 5.7 times 10 to the exponent of negative 2 kilograms, as that is the mass of the tennis ball. V is the speed of the ball, which would equal to 9.6 meters per second. R would be the radius, and that is equal to 1 meter, as using a diagram, the length of the two corners can be considered a diameter of a circular path that the ball travels in. Dividing the diameter 2 meters by 2 gives a radius of 1 meter. B would be the magnetic field strength and is equal to 1.5 times 10 to the exponent of negative 5 teslas. Putting the numbers into our variables gives a value of about 40,533 coulombs. Therefore, the charge of the magnetized ball is about 4.0533 times 10 to the exponent of 4 coulombs.
Kinetics and forces of Kai. Scenario 1 involves circular motion and centripetal force. A Kai ball is hit and takes 1.5 seconds to reach another player. During this time in the air, Dr. Young observes that the ball rotates with a frequency of 4.0 Hz. Given that the radius of the Kai ball is 3.25 centimeters, what velocity was the surface of the ball rotating at? If the surface of the ball is 20 grams, how much centripetal force is acting on the surface of the ball while it spins? We know that the mass of the surface of the ball is 20 grams, the radius of the ball is 3.25 centimeters, or 0.0325 meters. The time the ball spends in the air is 1.5 seconds, and the frequency in which the ball rotates at is 4 Hz, or 4 rotations per second. To find the rotational velocity at the surface of the ball, we can use the equation v equals 2 pi r over t. T is equal to the duration of each rotation, and it's equal to 1 over frequency. Frequency is 4.0 rotations per second, so we can conclude that the duration of each spin is 1/4 of a second. By plugging in radius and plugging in t, we can conclude that the velocity is 0.82 meters per second at the surface of the ball. To find the centripetal force acting on the surface of the ball, we can use the equation mv squared over r, where m is the mass of the surface of the ball, v is the rotational velocity at the surface of the ball, and r is the radius of the ball. By plugging in these values and solving, we get a value of 4.1 times 10 to the 2 newtons. Therefore, the surface of the Kai ball will experience a centripetal force of 4.1 times 10 to the 2 newtons while rotating with a frequency of 4.0 Hz. The second scenario for kinetics involves gravitational force and applied force. Elon Musk and Harrison are taking a trip around the solar system for a SpaceX mission. They decide to pack a volleyball to play Kai during their downtime on some of the planets they visit. After conducting research, the two of them played a few games on Pluto, Jupiter, and Earth. If Elon wants to serve the 0.28 kilogram ball with a velocity of 50 meters per second up 45 degrees east, and he strikes the ball for 0.2 seconds, what force does he need to strike the ball with on each planet? So we are given the mass of the ball, which is 0.28 kilograms, the time it takes Elon to serve the ball, which is 0.2 seconds, which is also the amount of time that Elon is applying force to the ball, the force of gravity on all 3 planets, the velocity right after the serve takes place, which is 50 meters per second up 45 degrees east, and the initial velocity before the serve, which is 0 meters per second. To find out how much force Musk needs to apply onto the ball during the serve, we first need to find out the acceleration during the serve. Acceleration is equal to v2 minus v1 over t, which, when we plug in the values, equals 250 meters per second squared up 45 degrees east. Next, we need to find out the vertical and horizontal net forces on the ball. F net is equal to ma, which is equal to 70 newtons up 45 degrees east. Next, we can use Pythagorean's theorem to conclude that 70 newtons squared is equal to F net vertical squared plus F net horizontal squared. Since the ball is being served at a 45-degree angle, we know that F net vertical is equal to F net horizontal. Therefore, 70 newtons squared is equal to 2 F net horizontal and vertical. After solving, we figure out that F net in the vertical and horizontal component are both 31.623 newtons of force. Since force applied is the only horizontal force acting on the ball, F net horizontal is equal to F applied horizontal. Therefore, F applied horizontal is equal to 31.623 newtons. To find out the applied vertical force on each planet, we know that F net vertical is equal to F applied plus Fg. Therefore, F applied is equal to F net V minus Fg. And since the vertical net force is also 31.623 newtons, we know that F applied is equal to 31.623 newtons minus the force of gravity. In a table I compiled all the data from all three planets. I found the force of gravity acting on the ball by taking the mass of the ball and multiplying it by the force of gravity on that planet, and then I took that value and subbed it back into the equation to find the force applied vertically on that planet. Lastly, I used Pythagorean's theorem and then tan to figure out the total force applied and what angle it was applied at. Therefore, to bring the ball to 50 meters per second up 45 degrees east, Musk must strike the ball for 0.2 seconds with a force of 46.7 newtons up 42.6 degrees east on Earth, 49.9 newtons up 39.3 degrees east on Jupiter, and 44.8 newtons up 44.8 degrees east on Pluto.
Energy and momentum. The law of conservation of energy states that energy cannot be created or destroyed, but only transferred from one form to another without any loss. This can be applied in Kai with the use of mechanical energy, or in other words, the sum of the kinetic and gravitational potential energies. When the ball is hit by a player, the ball has a small amount of gravitational potential energy initially, as the ball is not hit from the ground but at a specific height. In addition, the ball has a small amount of kinetic energy from the speed the ball gains from being hit. Eventually, the ball loses kinetic energy and gains more gravitational potential energy as it moves higher and higher in the sky until it reaches maximum height. At maximum height, the ball has gained its maximal potential energy while having zero kinetic energy. However, as it begins to decrease in height towards the catcher, the ball's speed increases, which causes potential energy before to convert into kinetic energy. As the player receives the pass, the ball is moving at its maximum speed. Scenario 1. If a person who is 2 meters tall hits the ball at a speed of 10.1 meters per second at the height of the person, what would the speed of the ball be when the person is about to catch the ball? Since we are given the height of the first player, which is 2 meters, the speed in which he hits the ball, which is 10.1 meters per second, and that he catches the ball, which means there is no kinetic energy at this point, we can then use the law of conservation of energy to isolate and solve for the height of the second player, which works out to be about 7.2 meters tall. Next, we can set gravitational potential energy equal to kinetic energy, and using our new height, isolate and solve for the speed of the ball when the player catches the ball, which works out to be about 12 meters per second. Therefore, the speed of the ball is 1.2 times 10 to the power of 1 meters per second when the receiving player catches the ball. Impulse is the change in momentum, which is equal to the force multiplied by the time. Linear momentum helps describe the motion of an object traveling in a straight line as the product of its mass and velocity. Impulse is a change in momentum and is known as the product of the force and the length of time during which the force acts. In Kai, the ball experiences changes in its momentum. At the start of the game, before it is hit, the ball is originally at rest 0 meters per second. However, when it is hit, the ball's velocity changes, causing the momentum to increase as well. This occurs because the rate of change in momentum is directly proportional to the change of velocity in the object. Scenario 2. Let's say a group of people wanted to play Kai and someone is about to strike the ball. The ball's initial velocity is at rest, or 0 meters per second. Its mass is 5.7 times 10 to the power of negative 2 kilograms, the mass of a tennis ball. Whatever speed the ball is hit, for example 7.7 meters per second, at to start the game is the change in velocity. Using the change of velocity in the ball's mass, I can multiply the two values to calculate for the impulse of the ball. Therefore, the ball's change of momentum was 4.4 times 10 to the power of negative 1 kilograms per meters per second. Jupiter has an acceleration of gravity that is greater than that of the Earth's. Hence, if the ball was hit at a specific height, the gravitational potential energy the ball has is a greater value in magnitude compared to a ball on Earth. Because of this, more gravitational potential energy is converted. Also, since the square of the speed is directly proportional to kinetic energy, the speed in which the ball lands on the player's palm increases on Jupiter due to the rising kinetic energy. Pluto has an acceleration of gravity less than that of the Earth. Hence, if the ball was hit at a specific height, the gravitational potential energy the ball receives is not as large in magnitude compared to a ball on Earth. Hence, due to a decrease in gravitational potential energy, there is less kinetic energy that is converted from potential energy. Also, since the square of the speed is directly proportional to kinetic energy, the speed in which the ball lands on the player's palm is less on Pluto than on Earth. These are the references that our group used to complete our Physics of Interplanetary Kai project. We hope you all learned more about the indigenous sport of Kai in relation to the physics behind it. Thank you for watching and have an amazing day.